All right, welcome everybody. This is 5.3 linear programming. We're going to be doing the same exact thing as we did in 5.1 and 5.2. Graph a linear inequality, shade, find corner points. The only thing different today is that we're going to take the corner points of the shaded feasible region and plug them into an objective function. And our goal is to either maximize or minimize the objective function, whatever the question is asking for. And the only way we can do that is by using the corner points, the intersection points of our linear inequalities. Okay, and this is called linear programming. So we can read through all this. Linear programming is a mathematical process that has been created to help management in decision making. The goal is to maximize or minimize a function. For example, you may want to maximize profit or revenue, and you also may want to minimize cost. A linear programming problem is one that is concerned with finding the optimal value, a max or min, of a linear objective function. This is the function we want to maximize or minimize in the form of z equals ax plus by. Okay. The objective function for a system of linear inequalities expresses the relationship among the variables involved in the concept to be maximized, or we can also say optimized, using the constraints of the inequalities. All right. A couple of theorems before we get started. Theorem 1, if the optimal value of the objective function in a linear programming problem exists, then the value must occur at one or more of the corner points. Again, we're going to take the corner points, the intersection points from our inequalities, and plug them into the objective function. Theorem 2, the existence of optimal solutions. If the feasible region for a linear programming problem is bounded, remember that a feasible region is bounded if we can draw a circle around it. Then it will have a maximum and minimum value that exists. If the feasible region is unbounded, meaning we cannot draw a circle around the shadings, and the coefficients of the objective function are positive, the minimum value of objective function exists, but the max does not. And if our feasible region is empty, it could happen. That is, there are no points that satisfy all the constraints, then neither the minimum value nor the maximum value exists. All right. And there's our steps for solving for finding our optimal solution. We will graph the linear inequalities, we will find the corner points, and we will test the corner points into the objective function. All right. Let's keep going. All right. Solve the linear programming problems by graphing the system of linear inequalities, find the corner points, and test the corner points into the objective function. Okay. So here we see they're giving us the objective function. So this is the objective function that we want to maximize. And of course, here is our system of linear inequalities. So this is everything we're going to be using. Okay. So first off, graph the linear inequalities, and we'll do the same method as last time. Let's just graph by x-intercept, y-intercept. It seems to be the fastest method. So we'll start with the first equation, 6x plus 3y equal to 24. We'll call this 1. (6x plus 3y equal to 24). X-intercept, y equal to 0. 6x equals 24. Divide by 6. X equals 4. Convert. 4 0. Y-intercept. Let x equal 0. 3y equals 24. Divide by 3, y equals 8. Convert. 0, 8. All right. So there's the x-intercepts for the first equation. Now let's graph the, find the x and y-intercepts of the second equation. Okay, I can do that right below. 3x plus 6y equals 30. Again, find x-intercept, find y-intercept. And you'll get 3x equals 30 and x equals 10. And then 6y equals 30 and y equals 5. Again, convert 10, 0. 0, 5. And now let's graph. All right. Plot the blue line first. The first equation, we have 4, 0, and 0, 8. So 4, 0, and then 0, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and then just connect. And I think these are all less than or equal to or greater than equals to, so these will all be solid. Okay, and then put that back at its regular size so I don't mess up like last time. And then we have x equals 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And x, y equals 5. 1, 2, 3, 4, 5. Yeah. Okay. And then I'll put the non-negative restrictions, which you see again are x greater than 0 and y greater than or equal to 0, which means that just keeps us in quadrant 1. We only care about anything in quadrant 1. All right. So okay. Now let's go ahead and shade, right? Which means we're going to need a test point. And again, we don't care about the green line. We only care about the blue and the red line. So we want to pick a test point either above or below both lines. And again, the easiest point to pick that's been working out for all of us is 0, 0. So we'll pick 0, 0. All right. Zoom in a bit. 3. All right. So, okay. For 0, 0, plug it into the first equation, 6x plus 3y. They're all less than, right? Yes. Six x plus 3y less than or equal to 24, which means we'll get 0 less than or equal to 24, which means we'll shade down towards 0, 0. So over here, this means I'll just shade down. Okay. And then next one, plug it into 3x plus y. Three x plus 6y equal to 30, less than or equal to 30. Plug in 0, you'll get 0 is less than or equal to 30. So again, both true statements, which means we shade down towards the true point of 0. Okay. Now, looking at our picture, we only want the feasible region, and the feasible region is where the shadings will intersect, which means we only want the corner points of that feasible region. So this means that here we have a corner point, down here we have a corner point, here's a corner point, and there's a corner point. Okay, and 3 of them are obvious to see. Maybe even the 4th one is. That one's already labeled 0, 0. This one is 4, 0. And this one, I'll just do it again, 0, 0. So I make it nice and neat. I'll erase this part. This one is 1, 2, 3, 4, 5, 0, 5. And this one, if my graph is correct, looks like it's at 2 and 1, 2, 3, 4. So 2, 4. Okay. But remember, you always want to prove if it's correct, so we can solve that in this system of equations. But I think we've done this problem on the last notes, and it does prove to be true. So these are the corner points. But just so I know that it's true, I'm going to do a real quick check. I'm going to plug 2 and 4 into both equations just to make sure it checks out. So if I plug 2 in, this becomes, well, 2 and 4. 6 times 2 plus 3 times 4, which is going to be 12 plus 12. And that equals 24. So it checks out there. But then, let me plug it in this one. And 6 times, that's 6. 3 times 2 plus 6 times 4 gives me 6 plus 24 equal to 30. So our point of 2, 4 definitely checks out, and it was clearly drawn on the graph. But remember, we have done this problem before in the last set of notes, so this has definitely been verified by a system of equations. If the point is not clear enough, then we will definitely need the system of equations to solve for it. Okay, so we have graphed the linear inequalities, we have done the test point, and now we are going to label the corner points, which I did already. Find the corner points, and I'll just point and say they're up here. Here's our corner points. Okay, which means next it says, take your corner points and test them in the objective function. Our objective function is p equals 3x plus 2y. So it is p equals 3x plus 2y. And our first corner point we saw was 0, 0. Our next one was 4, 0. Our other corner point was 0, 5. And our last corner point was 2, 4. Is that right? 0, 0, 4, 0, 0, 5, and 2, 4. Okay. Now all we have to do is plug these into the objective function. And we're looking for the maximum. So I'll get P equal to, if I plug 0 into the objective function, the whole thing becomes 0. If I plug 4 in for x and 0 in for y, we'll get P equals 12. If I plug 0 in for x and 5 in for y, we'll get 10. And then if I plug 2 in for x and 4 in for y, we're going to get what? 6 plus 12, right? 3 times 2 is 6. 4 times 2 is 8. So actually you'll get, so 6 plus 8, we'll get 14. And what we're looking for here is the maximum, which is going to be 14. Okay. Well, let's say it wanted the minimum as well. The minimum would be 0. I won't box it though, because this question wanted the max. Okay. And that is it. That is everything we did in 5.1 and 5.2. The only new thing is take these corner points and plug them into the objective function that they give us. That is it. Okay, let's do it again. This time we have a system of 5 equations, but only 3 really matter here. We know the bottom 2 are the non-negative restrictions, which keep us into quadrant 1. So technically we have a system of 3 equations. Okay, so we're gonna have to graph all these linear inequalities. Here is the objective function that we want to maximize and minimize. Okay, so we'll start with x plus y equal to 2. That's number 1. I'll try to use all my space as best as possible. X plus y equal to 2. Well, if you're going to go for x-intercept, y-intercept, this one is pretty easy to see that your x-intercept will be 2 and your y-intercept will be 2. So we have 2, 0, and 0, 2. All right. But I'm not going to graph these yet because I want to know what other points we are dealing with. I don't want to graph now, and then once we figure out the x-intercepts and y-intercepts for the other 2, that we realize we might have to change the intervals up. So it's best to find the x and y-intercepts first for all 3, and then if we have to change the intervals, we will. Okay, so there's number 1. Number 2, what am I working with? 6x plus 4y equal to 36. Okay, so go through the process. X-intercept, y equal to 0. 6x equals 36, x equals 6. So 6, 0. Y-intercept, x equals 0. And 4y equals 36, so y equals 9. You get 0, 9. All right. Third equation. 3. What are we messing with? 4x plus 2y equals 20. Again, same process. X-intercept, y equals 0. 4x equals 20. X equals 5. 5, 0. Y-intercept, x equals 0. And 2y equals 20. And y equals 10. 0, 10. All right, not bad. So now we can graph, and looking at my x values, I have 2, 6, and 5, so that is good. And then my y values, 2, 9, and 10. I think this graph is weird because it only goes up to 9. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'll just add our 10 in. There we go. All right. So plot the blue line first. 2 and 2, that's easy. 2 and 2, there it is. There's the blue line. Put that back to normal. Plot the red line, and 6, 0, 2, 3, 4, 5, 6. And then 0, 9. All right. And then plot the third one. This back to normal, and there we go. We have x-intercept at 5. 1, 2, 3, 4, 5. And then 10. All right. Perfect. So now let's go ahead and shade. Well, hang on. Let me put in those non-negative restrictions, right? So I can do that with this tool. All right, good. So there's that. And now we'll pick our most famous test point because we want a coordinate, a test point, now below or above all 3 lines. Well, what test point is below all 3 lines? Yes, that test point is again 0, 0. Okay, so 4, and we'll start with 1. This is x plus y is greater than or equal to. Huh. X plus y is greater than or equal to, and we're doing 0, 0. which means you get 0 is greater than or equal to 2, which is now false. Which means that since 0, 0 was not true, we are going to shade away from it, which means we're going to shade up. I mean, and yes, technically this line does go on. I didn't extend them longer, but yes, this line looks like that, right? But our shadings are only contained in the first quadrant. So I could just keep these shadings going. There we go. Okay. And now we'll test it into the red function, and the last two are less than or equal to. So we know that's going to be true for both of them. But I'll just write it down to do it. What did I have? Oops. 6x plus 4y less than or equal to 36. We'll get 0 less than or equal to 36, which means we'll shade towards 0. And the same for the green one. 4x plus 2y less than or equal to 20. So these both are true, which means we'll shade towards 0. Whew, so many colors. Okay, and now we want to look for the feasible region so we can find corner points. And let's see, scroll up. It looks like we're going to have corner points here, 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 and right there. And there's one more, which my graph doesn't look too clear, of where these two lines intersect. Okay. I'm going to erase this. And this corner point is what? 1, 2, 3, 4, 5, 6, 7, 8. Was there an 8? Well, that should have been 9. Let's see. Yeah, that should have been 9. My bad, but oh well, we're gonna have to solve this by system anyways. So, all right, so that is 0, 9. And then we have 0, 2. to 0, and then 1, 2, 3, 4, 5. 5, 0. And the last corner point is to be determined by a system of equations. And it's a good thing I color coordinated it, is because we know the green line and the red line intersect, and those are the lines we're going to use to solve for it. So I can do that down here. So the red line is 6x plus 4y equal to 36. And the green line is 4x plus 2y equal to 20. Okay, let's find that corner point. And what's the easiest variable to get rid of? I'm going to say y, because y has a least common multiple smaller than the least common multiple for x's. So 6 and 4 have a multiple of 12. 4 and 2 have a multiple of 4. So all I have to do is multiply the second one by -2. And I'll get 6x plus 4y equal to 36. And then I'll get -8x minus 4y equal to -40. Add them together, and we will get -2x equal to -4, and x equals 2. Now find y. And we'll use the first one, sure. 6x plus 4y equals 36. 6 times 2 plus 4y equals 36. 12 plus 4y equals 36. Move the 12 over, and 4y equals 24. And y equals 6. All right. Plus 12, yeah. All right. So, and I think my graph was off a bit, so that does not show 2, 6, does it? And if it does, it magically works. 2, 1, 2, 3, 4, 5, 6. It does. Weird. Okay. So this point, by a system of equations, which we just proved, is 2, 6. And again, I'll just point an arrow. I have the corner points listed above. Lots of corner points here. Okay, and now we want to plug them in to the objective function, 2x plus y, and see what gives us a max and a min. All right, 0, 9, 0, 2. Two, 0, 5, 0, and 2, 6. And our objective function is p equals 2x plus y. Okay, if I plug in 0 and 9, p will equal 9. If I plug in 0 and 2, p will equal 2. If I plug into 0, p will equal 4. If I plug in 5, 0, p will equal 10. If I plug in 2, 6, I'll get 4 plus 6, which will give me 10. Okay, we were looking to maximize and minimize. Well, 10 is our max, and it looks like we have 2 max. You can get a max at the corner point of 5, 0, or you can get a max at 2, 6. And then we have a minimum just at 2. And that is it. So, same exact process. Graph the inequalities, shade them by test points, and then now we find corner points and we plug them into the objective function. All right, there's that. And one more because it's the word problem, right? We have a word problem. All right. Example 3. A furniture manufacturing company manufactures dining room tables and chairs. The relevant manufacturing data are given in the table below. All right. So for tables and chairs, the assembly, it takes 8 hours to assemble a table, 2 hours to assemble a chair, and then there are 400 labor hours available per day to do this. Finishing, it takes 2 hours to finish the table, 1 hour to finish the chair, and there are only 120 labor hours available per day to do this. And then they give us the profit per unit. We'll make $90 per table and $25 per chair. All right. How many tables and chairs should be manufactured each day to realize the maximum profit, and what is the maximum profit? So this means we need to create our linear system of linear inequalities, and we also have to create the objective function. And all that information is given to us in the table above. So let's create our system of linear inequalities. And that is going to be that, what are we going to call this? I'll just do this. There you go. We're going to say tables are X and chairs are Y, right? So 8X plus 2Y, and the maximum hours per day to assemble a table and chair are 400. So we can't go over 400. So we have to be less than or equal to 400. Okay, and then for finishing, 2 hours to finish a table and 1 hour to finish a chair. And we are only given 120 maximum hours. Okay, and of course, you know what we have to add to this. This is a business model, which means we can't go below 0. So we add our non-negative restrictions. Behave. There we go. Okay. And then, what is the objective function? That is given as the profit per unit row on the labor hours per unit. And we will make $90 per table plus $25 per chair. Okay, now we have our system of linear inequalities. Let's graph it, okay? Let's graph it. So, number one, 8x plus 2y equals 400. So, x-intercept, y-intercept, right? X-intercept gives me 8x equals 400. And divide by 8, and that should give us 50, right? 50, 0. And then y-intercept, 2y equals 400, divide by 2, and y equals 200. 0, 200. Okay, like I said, don't graph it just yet because we want to find the x and y intercept of the next one so we can make appropriate intervals. All right. Next one is 2x plus y equal to 120. I got space below, right? Yes. And again, x-intercept, y-intercept. Two x equals 120, x equals 60. We get 60, 0. Y-intercept, you get just y equal to 120. All right. Okay, so let's go and graph. Let's make our intervals appropriate. X is 50 and x is 60. We can go by tens. Why not? Let's go by tens, right? Okay. For my x values. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And then y values are 200 and 120. We can go by 20s. We're just going to have to make an extension at the top. Because like I said, this graph is weird. It only goes up to 9. All right. 20, 40, 60, 80, 100, 120, 140, 160, 180. Extend this one just a little bit. 200. And now let's plot. 50 and 0, right there. And then 200, right there. Oh my goodness, make a straight line. Okay, and then let's switch that back, come here. 60 and 120. I can't make a straight line to save my life. Oh man. Okay. So we know that we're going to stay in quadrant 1, so I can probably highlight that a bit. Let's see. Let's just see. And okay, perfect. So we can pick our test point. We need a test point above a line or below both lines. And again, 0, 0 seems to be our best friend. That point is below both lines. And I'm just going to skip a step here because if I plug in 0, 0, we'll both get true statements here. If I plug in 0 here, you'll get 0 less than or equal to 400. And you'll get 0 less than or equal to 120, which means we'll shade down towards 0. Okay, shading's done. Let's find our intersection points, our corner points, and those happen to be right there, right here. Let's see, probably have to get really close here. Oops. So here, there, I think we're gonna need this one, and then we're gonna need right where they intersect. Okay, so 3 are easy to see. The other one we'll have to prove by a system of equations. Okay. So this one was 0 and 120. This one is our, it's not technically 1 because, we'll use it anyways. We'll have 0, 0. And then this one is 50, 0. And then this one we'll prove by a system. Do I have room? I have room above it. So for this one, we'll prove by our system of equations, and I'll make it 8x plus 2y equals 400. So right here. And this one was, what, 2x plus y equals 120. Let me make sure that's right. Okay, good. Now, solve it by using elimination method. We'll get rid of y, that's the easiest one. So I'll multiply this one by -2. We'll get 8x plus 2y equal to 400. And -4x minus 2y equals -240. We end up with 4x equal to, what is that, 160? 4x equals 160, and x equals 40. Now find y. We'll plug it into the first equation. That's 2 times 40 plus y equal to 120. 80 plus y equals 120. And y is going to equal 40. So this point is 40, 40. Proven by the system of equations. Okay. Oh, we still need more room because it says, what is the maximum profit? Well, we have to plug our numbers into the objective function. So I'll say step 3, I could probably fit right down here. 90x plus 25y. All right. Maximize profit. We know our objective is 90x plus 25y. And my corner points are 0, 0, 120 and 0, 50, 0, and 40, 40, I believe. There's just 4, right? 0, 0, 0, 120. Oh, 120. Yeah, oh, 0, 120. Yeah. And then 50, 0, 40, 40. Okay. Plug them into 90x plus 25y. If I plug in 0 there, you're going to get 0. If I plug in 120, 120 times 25, 3,000. If I plug in 50, 50 times 90, 4,500. And if I plug in 40, I mean, this one seems like the best bet, right? 90 times 40 plus 25 times 40. So these corner points, these make 40, 40 makes my maximum profit. 40 tables, 40 chairs. So this is max. Okay, there you go.